So we've seen that we can describe how you move around in space by something we call a metric. And then if we mess this metric up, you can get really crazy things happening. You can have discontinuous space, or you might actually have curved space. So Paul, what does this have to do with Einstein's original thought of mass and acceleration and gravity all being mixed into one?
Well, here's the basic idea. The idea is that the metric is actually set by mass. So if you know where all the masses are in some part of the universe, you can use Einstein's equations to calculate the metric, and it will be curved. And this is actually the explanation for gravity. Gravity is not a force, it's just a curve of the metric. So for example, we've seen by messing up the metric you can get things to move in circles. And that's exactly the explanation that Einstein came up with orbit. For normal Newtonian physics, we think of something going in an orbit as there's a force towards the middle, making it go in a circle. But what Einstein said is it's not like that. What's happened is the mass is not producing a force. The mass is changing space-time around it, so that the natural path, what we call the geodesic, the natural path of something, instead of being a straight line, is a curve.
So if something's going a curve, a rocket ship, for example, goes in an orbit around Earth, it's curved. But what about light? Light travels in straight lines, I think, going around the Earth.
Well, we've glossed over time in this. The real metric involves time as well as space. And it turns out that the curvature of the path of a spacecraft, it looks like it's pretty strongly curved, and of light, which is only very gently curved, there's a bit of gravitational lensing, so it's not perfectly a straight line. But in fact, in space-time, the curvature of the two are the same. But we'll gloss over that for the purposes of this lecture.
Okay, so this is the heart of what makes Einstein's theory of general relativity work, this curvature. But what does it have to do with cosmology?
Well, let's explain how it fixes the problem of the two masses.
Yep.
So let's say we have this ball, and in Newtonian physics, if I let go, it drops. And what we would explain that by there's a strange force coming up from the Earth. According to Einstein, once again, there's no force. All that's happening is the ball is following its geodesic, and its geodesic is to accelerate towards the centre of the Earth at 9.8 meters per second squared. And that's simply because the space-time in this room is curved a little bit.
Okay, so the ball is falling. When you drop it, it follows its geodesic. But you and I, we're sitting in chairs. We're not moving anywhere. What's going on there?
Well, of course, what's happening here is that my geodesic and your geodesic is indeed to fall towards the middle of the Earth. That would be our natural state. But there's a force that's holding us up. In that case, it's a force due to the springs or the foam in these chairs. That foam is compressed and pushing us up. So the only real force, there is no gravity force. The only real force is the force from the chair. And that's a force you can measure. You can actually see how much the chairs are compressed and the squashing of whatever you're sitting on. So that's a very real force. So this explains why acceleration and gravity are the same thing, that in fact there is no such thing as gravity, it's always acceleration. When we think of gravity, for example, making something go in orbit or pushing us down in the chair, it's not. These things are just following their geodesic, there's no force involved. When you depart from your geodesic, like us, there is a real force, but that's a force we can actually measure, it's the force of foam in our chair.
So it's kind of analogous to a centrifugal force, which is this force that we sort of is not really there, but we often like to describe it when we look at circular motion.
Yes, this is a centrifugal force is what we call a fictitious force. When you're driving down the road and the car suddenly goes to the side, you feel like you're flung to the opposite side quite strongly. It feels like a real force. But in fact, what's happening is you just want to keep going in the uniform motion in a straight line, and a real force is the side of the chair pushing you sideways, your seatbelt pushing you sideways. It's the same here. We think that gravity is a force pulling things downwards, but in fact the natural motion is to go downwards, and the actual force is what happens when you hit the bottom. And this explains why mass, that's inertia, resisting acceleration, the gravitational mass are one and the same thing.
Right. And so we're going to find out next time how this affects the whole idea of the universe and everything through how gravity interacts with cosmology.
That's right.